Hello. Hope you're surviving the pandemic okay. I've got these two critters here that are keeping me company during the pandemic. These furry creatures. That's Murphy in the front and Maggie in the back, 11 and 10 years old. And they had some recent health scares, but they're coming through it just right now, so they have a little moment of peace and happiness. Hope you guys do too. We're going to continue on with our, believe it or not, last test for Convergence of Series. And it's a big one. It's a good one. And it's nice and easy to use too. So what we're going to do with this fella is we're going to motivate it, maybe from something very familiar, and then we're going to practice it like hell. It's going to be really handy for a series of a particular form. So let's get into it. All right, so let's go with our good old, that's yellow, sorry, geometric series. This is the very first type of series that we considered, and if you remember, it looks something like the sum, n equals 1 to infinity, of some a, some constant a, times some factor r, also a constant, to the n minus 1. And this, we would generically call our an now in our new notation. That's our an, ar to the n minus 1. And we remember that this converges so long as r is less than 1 in absolute value. All right, so all I'm going to do for a geometric series, I have the result for convergence for that thing, but what I'm going to do is I'm going to look at a particular ratio here. I'm going to look at the ratio of an plus 1 over an. Now, an plus 1 is just simply going to that expression, and every time you see an n in the an, you replace it with an n plus 1. It's very easy. What I mean by that is it's a r to the, instead of the n, I'm going to go n plus 1, okay, minus 1, all over an, and an is just that expression, so it's a r to the n minus 1. Now, when I look at this, the a's clearly cancel. Okay, that a and that a, they're just constants, so a over a is 1, so they're gone. I've got an r to the n plus 1 minus 1. All right, so that's equal to an r to the n. And on the bottom, I've got r to the n minus 1. And of course, those are just their power functions with the same base, r, and the powers are only different by 1. So I can reduce that further into just r. Okay, the exponent n minus 1 just gives you r to the 1. So the ratio of successive terms of a geometric series is equal to that constant r. And of course it is. To get the next term in the series, you multiply the last series by r. That's what that's saying. Now, for a geometric series, if that r is less than 1, then the series will converge. So what we're going to do is take that idea that the ratio of successive terms being bigger than 1 or less than 1 for a geometric series gives you convergence. And we're going to adopt it for general series, and it basically carries forward in a very, very similar way if we look at the ratio of successive terms. The only difference is we look at the limit as we go to infinity in this process for general series. And using this reasoning, even though I haven't proven anything, using this reasoning, we build up our last test. So I'm just going to say here for general series, and when I say general series, I just mean some, any an, not necessarily geometric. We can adopt this reasoning. And the reasoning goes like this. Item number 7 in our grand list of tests. Okay, this is the ratio test. Ratio because it's talking about the ratio of successive terms. So, if I have some series, an, if the limit as n goes to infinity of the ratio of successive terms an plus 1 over an is equal to some limit L, and if L is less than 1, remember the L is kind of the placeholder of this idea of R in a geometric series. So if the ratio of successive terms is less than 1, we'd say the sum of an converges. If, on the other hand, L is bigger than 1, then the ratio of successive terms, I get a sense that the thing might be growing. Okay, so L bigger than 1, or actually L equal infinity, then the sum of an that diverges. And finally, if L equals 1, this is tricky. We have no information. We don't know what it's doing. So we can make no conclusion if we end on the unlucky value of L equals 1. This whole thing is called the ratio test. And just like all the other tests for convergence of series, it's got its little wheelhouse, places where it works really, really well, really easily, gives you a result very quickly, and other places where it doesn't work at all. All right, so we're going to start off with what I call the real wheelhouse of the ratio test. It's parts of the expression an that give you hints that the ratio test is going to work, and it's where it really is elegant, let's say. And that place is all about factorials. So if you have factorials in your an, probably the ratio test is going to be used. And I want to do a quick little run through of some properties of factorials, just so we all are comfortable with them. And so if you remember, let's say 6 factorial, what that means is 6 times 5 times 4 times 3 times 2 times 1, and so on. And if I did 6 factorial over, let's say 5 factorial, 5, 4, 3, 2, 1, well, then of course I just get all of this stuff canceling, and I end up with a 6. If I have 6 factorial over 4 factorial, then I get 6 times 5 times, I can just write it as 6 times 5 times 4 factorial. Write that as 4 factorial. Those are gone. And you just get 6 times 5. Or 30, of course. I might as well write it in, what the heck. 30. Now, we often, when we're using an as a series term, we don't quite see 6s and 5s and 4s, but what we do often see is things like n plus 1 factorial over n factorial. You might imagine that occurring if you do the ratio of an plus 1 over an somewhere. You might see something pop out like this. And the reason why the ratio test is so wonderful is because these things reduce very easily. N plus 1 factorial is like saying n plus 1 times n minus 1, n minus 2, all the way down to 2 times 1. But I can similarly write it as n plus 1 multiplied by n factorial. Just pull off the leading term and then leave everything else. And then on the bottom, I've got an n factorial. So, what do we do here? That equals, well, those are obviously going to cancel, and we just get an n plus 1. Wrong color. Get an n plus 1. If I had, let's say, n plus 2 factorial over n factorial, well, very, very similar. Here's the trick. You take the bigger of the two expressions, n plus 2 versus n. Obviously, n plus 2 is bigger. You start pulling off terms, n plus 2, and you start counting down, multiplying things together until you hit the lower one. And there, I've done it, n factorial. And you write the n factorial in the bottom, you cancel the terms, and here we are left with n plus 2, n plus 1. You're going to see that operation a whole lot in this next little section. So I want you to get good at it and get comfortable with that factorial operation. Okay, so we're going to do a simple one first, and yeah, see how it goes. Let's get a new sheet going here. Go back for a sec. Formulate this limit. Get the limit L. We just found L equals 0. If L is less than 1, then your series converges. If L is greater than 1, the series diverges. We found L equal to 0, okay? And so 1. All right. If L is bigger than 1 or L equals infinity, then we say the sum of an diverges. All right, so example. Does blank converge or diverge? Same old question. But now we're going to put a factorial on, 1 over n factorial. Does this thing converge or diverge? And it might not be obvious, but if you look at that thing and you think about all our previous tests, the integral test, the limit comparison test, the comparison test, all these ones, they really just kind of don't work for 1 over n factorial. This is where the ratio test really does work. Okay, so let's give it a go. Solution. Use the ratio test. And so if I want to use the ratio test, then I have to evaluate this limit of an plus 1 over an in absolute value. All right, an plus 1. You take the expression up here. That's my an. If you want an plus 1, you take the n, replace it with an n plus 1. 1 over n plus 1 factorial. And you divide by an. an is 1 over n factorial. Now, a couple of important points here. First off, n plus 1 factorial is not n factorial plus 1 factorial. That will be distributing the factorial across n plus 1. We cannot do that. They are not equal to the same thing. n plus 1 factorial is n plus 1 times n factorial, if you want to rewrite it, but it's not n factorial plus 1 factorial. That's the first thing. The second thing is you look at this expression here, and it's a little bit what I'd call awkward. I have a fraction divided by another fraction. What I'm going to do in this situation is rewrite it in an equivalent form by multiplying it by reciprocal, one sec, sorry. Reciprocal of the denominator. All right, so what I'm going to do is rewrite this as the limit, as n goes to infinity, 1 over n plus 1 factorial, and then just take the bottom and flip it. So that's n factorial over 1, right here. Now, this often happens. If you look at all the terms are positive, and so those absolute values are really doing nothing. It doesn't matter whether they're there or not, all the terms are positive. And if they're all positive, I can just basically get rid of the absolute values. Now, if there was an alternating part to this series, then the absolute values would matter, but they don't right here. All right, so we're good. This equals, limit as n goes to infinity, n factorial over n plus 1 factorial. And now you probably noticed that we're in the exact same location that we just were talking about before we started this example, and that is I've got a ratio of 2 factorials. Now, it turns out the bigger one's in the bottom. That's not a big deal. You look at the two of them, you take the bigger one, n plus 1 is bigger than n, and you expand terms until you get to the lower one. Now, this is just n plus 1 n factorial. Okay, there's just a difference of 1 in the 2 in the top and bottom there, so there we go. This is equal to the limit as n goes to infinity of 1 over n plus 1. And now I go all the way back to my old days in Math 106, and I think, okay, what does this do as n goes to infinity? The bottom grows, the top does not. You get basically 1 over something infinitely large, and that goes to 0. Okay, what does that mean? It goes to 0. L equaling 0 gives us the conclusion of convergence. So again, I'm going to write this in a way that has structure and always calls upon the proper test that I'm using for my conclusion. So I would make a little statement here. Since L equals 0 less than 1, then by the ratio test, the sum of 1 over n factorial converges. All right, that's how it works. We're going to try another one now. Getting new slides now. Right here. Does the sum 1 over 2n factorial converge or diverge? And again, we're going to use the ratio test. Anytime you see a factorial in the expression, you're almost always going to use the ratio test. That's the rule. All right, so let's try the ratio test. Always start the same way. Limit as n goes to infinity. an plus 1 over an. Formulate this. Be very, very, very careful doing an plus 1. All right? I'm going to show you a thing that people will do, probably like 70% of the time, and screw up a question like this. So we're going to try to pay attention and not do it. an plus 1 means go up to the expression, this thing, that's my an. Take the n and replace it with an n plus 1. Do it with brackets, too. So it's the limit of 1 over. Now, here's what people would do if they're being careless. They'd go 2n plus 1 factorial. That's not it. That's not an plus 1. What it is, let's get rid of that, is 2, and then you replace the n with an n plus 1. But the whole thing is multiplied by 2. So it's 2n plus 1 factorial. And it's different because that's actually 2n plus 2 factorial, not 2n plus 1 factorial when you expand it out. Now we divide by an, but we know that dividing by an is like multiplying by the reciprocal of an, and I can do that all in one step. So I can just go 2n factorial over 1. That's the reciprocal of an. So this is not 2n plus 1 factorial. That's our little thing to keep in mind. All right, well, what do we have here? Limit as n goes to infinity, 2n factorial up top. And on the bottom, when I expand that out, I get 2n plus 2 factorial. And then basically it's just look at the two of them, pick the bigger one, write the terms successively reducing until you get to the smaller of the two expressions on top and bottom. Okay, and that's going to give me this 2n factorial over 2n plus 2, 2n plus 1, and then down to the 2n factorial. And so those are going to go. And now this is getting to be pretty straightforward. N goes to infinity of 1 over 2n plus 2, 2n plus 1. The limit of that is equal to 0. Again, the denominator grows, the numerator does not. So that has a limit of 0. And same conclusion now. Since L equals 0 less than 1, by the ratio test, the sum 1 over 2n factorial converges. Probably obvious from the first question that this is going to converge. It converges more quickly than the previous question we did. That bottom is growing more quickly. So if the first one converged, this one sure as heck should converge as well. All right. We're going to keep on with examples because that's the best way to get good at this. I've been mentioning a lot about factorials. We just did 2 examples with factorials. There is another kind of an expression that works really well with the ratio test that we see often in series expressions. And that is some kind of exponential function where the n is in the exponent and then we have a base that's some number. So I'm going to give you an example. We're going to see how the ratio test will work in this instance. So does the summation n equals 1 to infinity of n times 2 to the n over 3 to the n converge or diverge? Okay. The new thing is right in here, it's the 2 to the n and the 3 to the n. These are those exponential functions, base 2 and base 3. The ratio test works really well because successive terms, an plus 1 over an, are going to cancel really nicely for functions that look like this. Okay, we'll just see it work in action and you'll get used to it. So, solution is use the ratio test. See how it works. Always the same way. Take the limit as n goes to infinity of an plus 1 over an in absolute values. Now, an plus 1 means take every term and replace the n with an n plus 1 and use brackets if you care to. Usually is a safe thing to do. You don't always need them, but it never hurts to put them in. Okay, there's an plus 1. We multiply by the reciprocal of an. Okay, and so that's going to give us a 3 to the n on top and 2 to the n on the bottom. Okay, now the next thing I want to do, again, all those terms are positive, so I don't really need the absolute values. They're not hurting anything, but at this point I can pull them out if I want to. The other thing I'm going to do is I'm going to look at terms that are similar in their structure. That is, they have base 2 or base 3, or they are just the n plus 1 of the n, and I'm going to group those on top of one another. And I'm going to set myself up to recognize some cancellations that might happen. All right. So again, just a reminder, this term I multiply by reciprocal, and that's where I get that expression. Okay, so I'm just going to rewrite this and pull out my absolute values. I see a 2 to the n plus 1. Okay, so I've got u dealt with. And I see a 2 to the n down here, and I'm going to write that just underneath it, 2 to the n. I also see a 3 to the n up here, and a 3 to the n plus 1 down here. So I'm going to write that next, 3 to the n, 3 to the n plus 1. Finally, I have, an n plus 1 and an n. So I'm going to write those two, n plus 1 and an n. Okay, now, look at this term here, 2 to the n plus 1 over 2 to the n. The base is the same. The exponents differ only by 1, so this is like 2 to the n plus 1 minus n. And then I have 3 to the n minus n plus 1. But the upshot of it is I have an extra 2 on the top, and I have an extra 3 on the bottom. So that's 2. N plus 1 minus n is 2 to the 1. N minus n plus 1, this term right here, is like a 3 to the minus 1. That's just the extra 3 in the denominator. So I'm going to put it right there. 2/3 n plus 1 over n. I can take that 2/3 out, and I'm left with n plus 1 over n. And I want the limit as n goes to infinity of that term. And you can think conceptually about this. I mean, as n is, let's say, 400 billion, that ratio would be 400 billion and 1 over 400 billion. That's pretty damn close to 1. Alternatively, it's a ratio of two polynomials in n. They're linear terms, so degree 1 polynomial, where the ratio of the leading coefficients is 1 over 1. Or, if you don't like that argument, I can write it as 2/3 times the limit as n goes to infinity of n over n plus 1 over n over n over n. That is, divide the top and bottom by n. And that term goes to 0, that term goes to 1, that term goes to 1. And you end up with 2/3 times 1 plus 0 over 1. You get 2/3. The whole limit of that is 1. N plus 1 over n, that limit is 1. So you get 2/3. Now, at this point in the game, it can feel like we've just completed a limit calculation. Sometimes that triggers our brain to say, you've done the question. You got a number, you've done the question, move on. You're not done the question, though, right? What are we doing? We're using the ratio test to talk about the convergence of this particular series. And we've formulated this limit. And this limit, of course, remember, gives us the value L. And then from that, we use the ratio test to make the conclusion. So here, I say since L is equal to 2/3, which is less than 1, that critical threshold value of L, then by the ratio test, the sum of n times 2 to the n over 3 to the n, that thing converges. Okay. All right, we're going to do one more example here. Scroll down. Just to really hard code this technique in. Does the summation n equals 1 to infinity do n factorial over 10 to the n converge or diverge? And a lot of what we do when we look at these series is we have an expression on top and bottom, and we look at the ratio of these things, n factorial and 10 to the n, and we ask ourselves, oh, I wonder which one grows more quickly. Is the factorial operation on n, does that grow more quickly as I go to infinity? Or does an exponential function of base 10, 10 to the n, does that thing grow more quickly? They both grow pretty quick. So when I look at the ratio of these two things, it really does get at the heart of which of those two functions, the factorial or the exponential, which dominates. All right, well, this is composed of two things that I know the ratio test works well with. That's an exponential function and a factorial. So this is doubly suggestive that the ratio test is going to be the one to try. Oh, ratio test. Ratio test always starts the same way. Limit n to infinity, an plus 1 over an, absolute values. It's not going to make a difference here because all the terms, again, are positive. Okay? an plus 1 says, take the expression, replace your n's with an n plus 1. Multiply by the reciprocal of an, and that is, I have the reciprocal of the expression up here as 10 to the n over n factorial. All right, and then we're just off to the same old math tricks that we've been using. Stack the things that are similar, get rid of the absolute values because all terms are positive. 10 to the n over 10 to the n plus 1. Then I have an n plus 1 factorial over an n factorial. By the reasoning I used in the last example, the first term gives me a 1 over 10, and then the second term gives me an n plus 1 times n factorial over n factorial. That allows me to reduce that expression into just a 1 over 10, which I could bring outside the limit if I wanted to, times n plus 1. Okay, something a little bit different here now. 1 over 10, limit n to infinity, n plus 1. Now the 1 over 10 is all well and good, but the limit as n goes to infinity of n plus 1, well, as n goes to infinity, n plus 1 also goes to infinity. And whether I multiply that by 1 over 10 or not, it's still going to infinity. So there we go, I get infinity equaling my L. That is, the limit does not exist, but it doesn't exist in a specific way where the limit becomes, or the expression becomes infinitely large as n goes to infinity. All right, remember the ratio test. Bring it back to this example we're working on. We got an L equal to infinity here. Since L equals infinity, by the ratio test, the summation of n factorial over 10 to the n diverges. That's how it works. Ratio test is absolutely wonderful for all questions that involve the convergence or divergence of series that involve exponential functions and factorials. That's where they work wonderfully, but they also work in a few other instances as well.